Welcome to today's Explainer. We're jumping right into something absolutely mind-blowing today. We're going to look at how one single, incredibly elegant engineering marvel is actively solving two completely different human challenges. And we're talking opposite ends of the size and weight spectrum here. It's really a story about mastering the invisible.
So think about this. What connects a life-saving artificial heart to a massive, multi-ton city train? I know, it sounds like some bizarre riddle, right? Like, how on earth could a delicate medical device share its core DNA with heavy urban infrastructure? Well, the secret lies in mastering the invisible forces of magnetism to completely eliminate mechanical friction. Okay, let's dive into this.
We're going to start our journey at the micro scale. I want you to really picture the environment inside the human chest. It is microscopic, delicate, and incredibly fragile. Now, for years, medicine has used devices to assist the left ventricle, just trying to keep feeling hearts pumping. But as we know, the human heart is a highly complex, beautifully balanced system. And sometimes, just assisting half of that heart simply isn't enough to save a life.
The stakes here? They're literally life or death. Up to 20%, that's 1 in 5 patients who get a left ventricular assist device, actually end up developing right ventricular failure. That staggering statistic proves there is a massive, vital need for a true, total artificial heart that helps both sides. But here is the absolute engineering nightmare. How exactly do you build a tiny mechanical pump that runs non-stop inside a human body without the mechanical bearings wearing down, or worse, physically crushing delicate blood cells?
Well, the elegant answer to that nightmare is something called a self-bearing motor, or SBM for short. Get this, in an SBM, the motor is the bearing. It uses highly controlled magnetic force to simultaneously rotate and suspend a rotor right in midair. There is absolutely zero mechanical contact. And that brings us to our main theme today, the frictionless force. By eliminating physical contact, you stop mechanical wear and tear, and more importantly, you protect those fragile blood cells from being damaged.
Now, what's really interesting about this slide is seeing how this actually comes together in the real world. Take a look at this experimental setup. Over on the left, you've got the fully assembled unit. And on the right, you can see the separated stator with all those complex copper windings. It uses a double-sided stator design. Basically, imagine two of those stators acting like a sandwich, with a super thin slice rotor suspended perfectly in the middle. It gives you a massive surface area for high torque without taking up much space at all.
And the magnetic forces generated by those copper windings are just insanely precise. In lab tests, these invisible forces let that tiny floating rotor spin up to a massive 3,200 times a minute. But it's not just spinning out of control. The system actively manages the rotation, the up and down movement, which engineers call axial translation, and the tilt. And honestly, the most beautiful part of this whole mathematical design, there's zero interference. It controls translation and tilt entirely independently to keep it perfectly stable.
Okay, so how does this actually translate into a real medical device? Check out this exploded schematic of a maglev pump for a total artificial heart. You can clearly see the permanent magnets and the stator coils right there. Blood flows in and passes completely harmlessly right through the holes in that suspended rotor yoke. The impellers then push the fluid outward using centrifugal force. It is a 100% frictionless pump. It's moving life-sustaining blood using nothing but invisible magnetic fields.
All right, so we've seen how this frictionless magnetic levitation works and literally saves lives down at the millimeter scale. But right now, we're going to do a massive narrative zoom out. We're taking these exact same physics, eliminating mechanical contact with perfectly timed magnetic pulses, and taking it from the tiny, delicate human heart all the way up to the massive, heavy, loud scale of urban transit.
To bridge this gap, just think about how we normally move big vehicles around. Traditional trains rely on rotary motors, which means you need this messy, friction-heavy system of gears and axles and wheels just to convert spinning energy into forward motion. Linear motors, they bypass all of that. They provide direct forward thrust. It's literally the ultimate direct drive because you're stripping out the entire mechanical middleman.
To really get a mental picture of how this works, I want you to imagine taking that tiny circular heart motor we were just looking at and physically unrolling it. Just picture cutting that metal ring and laying the stators, the coils, and the permanent magnets perfectly flat on the ground, straight down a line.
And this brilliantly illustrates exactly what that looks like. When you unroll that motor along a train track, you get a direct drive system, specifically a long stator, permanent magnet linear motor. Notice how the stator coils are just sitting horizontally right along the guideway. The train car above it gets pushed forward using the exact same magnetic repulsion we just saw working inside a chest cavity. And bonus? That repulsive force actually provides lift, which makes the vehicle effectively lighter on the track.
So by putting these permanent magnets into this primary linear configuration, engineers completely solve the massive efficiency headaches you get with old-school wheel-based transit. This setup gives you a really robust, simple mover. It drives down costs, delivers incredibly high efficiency, and packs a massive amount of thrust. And it does the whole shebang simply by getting rid of the energy loss and the mechanical wear of physical friction.
The engineering consensus on this is pretty much crystal clear at this point. Direct linear drive motors give you higher dynamic performance, improved reliability, significantly lower noise, and way better efficiency. We are driving home that frictionless motif one last time here. Because preventing mechanical wear, cutting out grinding noise, and stopping heat loss, it works universally. The laws of physics literally do not care if you're protecting fragile blood cells in a patient's chest or hurtling a massive multi-ton train full of commuters across the city. The frictionless solution is exactly the same.
Which leaves us with this final, rather provocative thought to wrap up today's explainer. If magnetic levitation can seamlessly handle both the microscopic, delicate constraints of the human heart and the massive, heavy demands of a city train, where else is friction going to become a thing of the past? Seriously, take a look around your world today. Look at the machines you use every single day and ask yourself, what other everyday objects are just waiting to be completely transformed by the invisible power of magnets? Thanks so much for joining me today. Keep asking those big questions, and I'll catch you next time.